Welcome. This is a new lesson about the derivative test, and this is a very important point because this is the main concept for derivative-based optimization. So there are several types of optimization method. Among the most commonly used method is derivative-based method, and to learn about these derivative-based method, you need to understand derivative test. Other types of optimization include, for example, heuristic or stochastic, but one of the most commonly used optimization method is derivative-based method, and that's why we are doing this lesson. So this lesson mainly will do like conceptual understanding. So we will understand some main concept in derivative-based optimization, like for example, what are critical points, what are singular points, and what is the first derivative test, what is the second derivative test. And then we will apply these concept to solve some fundamental problems, some FE problems basically. And then in uh, subsequent videos, we will like the concept and this fundamental skill that we use. We will use these concept and fundamental skill to solve simple optimization problems. And later I will show you the practical application just to explore it, not to have like hands-on experience, like to have hands-on experience in these models, and for example like to use these optimization to calibrate a model, or to use these optimization method to design a remediation system or design any system. That will be in other courses, yeah, not in this course. This course mainly focus on the conceptual understanding and fundamental skill, with some critical thinking exercise and just exploring some practical applications. Yeah. So let's just get started with part one of this lesson. So part one is about singular and critical points. Like what are these? Like why something like this would be important, like singular point or critical point, and why are we studying these things, or why are these things important? So in this lesson, by the end of this lesson, you will understand like the meaning of singular point with respect to derivative-based optimization method, and you will understand like when your function has singular points, and derivative-based optimization method might not be your best choice. You might go for like heuristic or stochastic or something like this. We will apply derivative test to identify and classify critical points of a function. So critical points of a function, that's like a local minimum or a local maximum. And optimization is basically like you are trying to find, like you have an objective function and you are trying to find the maximum or minimum value in this of this function. And we can do this using something called derivative tests. Yeah. And then we will practice derivative test problem for FE exam. Basically, that's like by the end of this lesson, you'll be practicing some of these problems. Okay, let's look here at this function. So basically, like, let's just study this function here before. So we have a function here. What is going on here? So we have this function. Yeah, this is like our function. This is like the derivative of this function, and we can evaluate this derivative at any point. Uh, we can evaluate this derivative at any point. So like this function here, here is like an endpoint. For example, here is another endpoint of the function. But you see these guys here, that is called like a local minimum. Yeah. See this guy here, that's called the local maximum, because you see the function keeps increasing, so the slope is positive, 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 until it goes to the top, and after it goes to the top, it start going down again. So positive, negative. And what is here? What is the slope here? The slope here is 0. So the slope at like this maximum point is 0. What is the slope here at this minimum point? The slope, the rate of change of the function is 0. Here is another minimum point, like another local minimum point. Again, what is the slope here? The slope here is 0. So the slope here before this is like negative, the slope here is positive, and the slope here at this turning point is 0. The slope here at this like local point is also 0. So wow, we reached a very important conclusion that giving like a function at these what we call like critical point, like local min or local max, the slope will be 0. Like so this guy, so this is the derivative of this function will be equal to 0. So if I set like this guy is equal to 0 and I find like the root of these equations, yeah, where like x is equal to 0, for like the derivative of this function, I will get this guy here, I will get like this guy here, I will get this guy here, and I will get this guy here. What else I'll get? I'll get this guy here. Yeah, because you see the slope here is also 0. What is this guy? This guy is neither like a local minimum or like a local maximum. So this is a minimum because this is a minimum, this is a maximum, this is a maximum. Why? Because this is not like, but this is called like an inflection point. Like the slope here is 0 because like this is an inflection point. So you have like a function, the function is like increasing, increasing, increasing. And then here the slope is 0, but then after this it continue increasing again. Versus here the function is decreasing, then 0, then increasing. Here the function is increasing, 0, decreasing. But here the function is increasing, and then 0, and then increasing again. So this inflection point, that is how like they are characterized. They could also have a slope of 0. Not necessarily, but they could also like have a slope of 0. Okay. So this is the main concept that we'll need to learn. Like what is like a local uh, uh, minimum and local maximum of the function. What is the global minimum or global maximum? The global minimum is like giving this domain like starting from here, yeah, ending like until here, like this range of my function. Oops. Like starting from here until like here, yeah. What is the global maximum? So the global maximum in that case it will be like this guy here. That's the maximum value of this function. So if this is like an optimization problem and I want to find the maximum value, like what is the maximum, for example, contaminants that we can remove, that would be this point. If this is like a minimization problem, what is the global minimum? Minimization problem, for example, I have a design and I want to optimize the cost of this design to find like the minimum cost. So what would be the global minimum? It will be like this guy. So I have like, this is the local minimum. Here is another local minimum. The maximum of these two is this guy. So that is the global minimum. The global minimum or global maximum could also be the endpoint. Like for example, like just for the sake of argument, if this line extend all the way till here, yeah. So in that case, what will be the global maximum? So the global maximum, we check like this critical point, like this critical point here, this critical point here, and then we also need to check the endpoints. Like we need to change this endpoint and this like endpoint. So this guy is obviously larger than this guy. This guy is obviously larger than this guy. This guy is larger than this guy. So the global maximum in that case would be this guy. So this is a global maximum. This would be just like a local maximum. That would be another local maximum. And here that would be like a local minimum. That's a local minimum, but that's also like the global minimum. Yes, this local minimum is the global minimum because this is the smallest point in my function. So basically, that is what we will learn in this lesson. We will learn how to find like these critical points. Yeah, how to find these critical points and inflection points. So critical point is like when the slope is 0. Yeah. And then here we know that, for example, like we can classify these critical points. So I can say this is a minimum and this is a maximum because I can see them. Like I plotted this graph and I can see it. But we will learn also how we can use the second derivative. Yeah. So the second derivative of this guy to, without plotting anything, you can tell, okay, this is a minimum, like this critical point is a minimum, this critical point is like an inflection point, or this critical point is maximum. Yeah. Okay. So that's basically what we will learn in this lesson. Like first part, how to use the first derivative or the first derivative test to find like a critical point, and then how to substitute this critical point in like this in the second derivative to know whether this critical point is like a mean, max, or inflection point. Yeah, or an inflection point. Okay, so basically that's the outline. But before we do this, let me show you when these derivative-based method will not work. Like if you look at this function, you might notice something about it. Like this function is first of all continuous. There's no discontinuity in it. And second, it is smooth, like you don't have any sharp edges. And third, you don't have any abrupt change, like a ridge. Like you don't have something that looks like this. That's like you have like a function here, and then suddenly it goes something like this. And sorry, like you have a function like this, and then you don't see anything like this sharp ridge. Yeah. And that is the conditions you need for these derivative-based method to work. If you don't have these conditions, then these derivative-based optimization method might not be the best choice, and you might need to use like a heuristic or stochastic. We like to use this derivative-based method because they are computationally more efficient than other method in terms of like your number, like especially when you solve these things numerically and how many function evaluation you need to reach a solution. Yeah. Okay. So let's just like look here. Let me delete this guy. So like you see this guy here, this is called like singular points. So singular point are like, for example, like that's an example of a singular point. So singular point here, this is like a cusp or like a sharp edge. So basically this is where you find like an abrupt change. So that is the definition, like uh, one type of singular points is that when you see this sudden change in your function. So your function is here, and then you see the sudden change in your function, not the smooth transition. And that is this sudden change in direction, making it impossible to define a derivative. Let me show you. Like so here, for example, okay, I have like a function that looks like this. I can define like the derivative. I can define like here. I can find the derivative here, like the slope of this line, which would be 0. Okay, and I can, but here, like, how could you define this guy? Like, this guy could be here, could be here, could be here, could be anywhere. It's actually infinite. Like, there's no, I cannot define my derivative here. And let's look at here. Like, so this function, which I plotted here, this is y over x to the power 2 over 3. The derivative of this function, you have like x here in the denominator. So if you substituted x equal to 0, you are dividing by 0, so you get like your derivative here is infinity. So I cannot find like the derivative. I cannot find the rate of a change at this point. It could be this, it could be this, it could be this, it could be anything. Yeah. Versus a smooth function, there is only like at a point, like I have this point, there is only one derivative. Like there is only one slope which I can define, but here there are infinite of them. Other example would be this absolute function. So absolute functions, this will, like if you have like -2, for example, it will give you 2. That's an absolute function. The derivative of the guy would be something like this. Again, here you have x in the denominator. So if you substitute it here, x is equal to 0, you get this is equal to infinity. And again, you have the same problem. You cannot, there are infinite derivative. You cannot find derivative. So when you have these types of function like singular points, so these are called singular points, then these methods cannot will not be effective. Yeah. This is another example of a singular point where you have this sudden change in your function. It's called like a vertical tangent because again, you cannot basically find the slope here. So this would be like a function like this. That would be the derivative of this function. Again, here is like 0, and then you will have the derivative at this point will be infinity because why the derivative here will be infinity? Because the tangent line at the point is vertical, so the slope will become infinitely steep. That's basically why. Yeah, and this will resulting in undefined derivatives. Other example is that you have this discontinuous function. Your function is not continuous like this. So here, this is an example of like smooth and continuous function. This is an example of a discontinuous function. This is an example of like a vertical tangent, and this is an example of cusps or sharp corners. Okay, so let's just here look at this guy here. Yeah, so let's review what we did. I'll just keep repeating again and again because I know for some of you this might be like a new concept. So here I have this is like this is oops. I have this guy here, that's like an endpoint. I have this guy here, that's an endpoint. I have, like you see here, I can put like a point here, that's like where the slope is 0. Slope equal to 0. And that is like a local maximum. I have here, this is a local minimum, although the derivative is undefined, but still a local minimum. I mean, I cannot use a derivative-based method to find this point for me, but I can use other methods. So this is still like a local minimum. Here, this is still a local maximum. Here you got another local minimum. Yeah, so here you got like another. So this is like local minimum. This is local minimum, and this is local maximum. Yeah, and this is like my endpoint here, and this is my endpoint here. So if I asked you, for example, what is the global maximum of this function? So the global maximum, that would be like this guy, because this is the largest value for this function. So if I want to maximize this function, that would be here at this point here. Yeah. If I asked you what is the global minimum of this function, so the global minimum of this function, it would be, let's see, that could be little. So that could be either like this endpoint here, like, so we have this guy here, we have this guy here, we have this guy here. Which guy is like, and like also this guy here, yeah. So which guy is the smallest of these guys? So maybe like see, this one is smaller than this one, and maybe this one, so maybe it is this one, but it could be also one of your endpoints, and that's why you always need to check the endpoint. Okay, so this basically just some conceptual understanding of what we mean by local minimum and local maximum, global minimum, and global maximum. With example, like if this is still unclear until now, be patient with an example. Like when you start solving an example, this concept might be more clear. So here, basically, this is just like to repeat here. Let's repeat what we did. I will repeat again and again and again until like you become familiar with these concepts. So here, this is an endpoint. This is like another endpoint. Yeah. Here, this is a local min. This is a local max. This is like an inflection point, like a critical point, inflection point. This is a critical point, local maximum. This is a critical point, local minimum. Yeah. Now here, this is again like the definition of critical points. That is like the definition of critical points. That's when f of x is equal to 0. Like this is where you get like all your critical points. So in that case here you have 1, 2, 3. Yeah. F of x here is not equal to 0. F of x here at this point is undefined. But still, this is like a local minimum. So here, if I asked you in this function, what is your global maximum? So your global maximum, it could be either like this local maximum or one of these two endpoints. So in that case, this guy is larger. So basically, that's your global maximum. If I asked you what's your global minimum, so you have to check like this guy, and your two endpoints. So this guy is smaller than this guy. This guy is smaller than this guy. This guy is smaller than this guy. So this is basically your global minimum. Yeah. So just like if this is still like terminology are unclear to you, you can pause the video and like look at them. But now at least you are familiar with this terminology. Like for example, like you're working with your colleagues and you find somebody saying, "Oh, I couldn't calibrate this model because it has a lot of local minimum region in my search domain and I couldn't use derivative based method and I have to use like stochastic method." You would know what they are talking about. Yeah, because in optimization your objective is to find like global maximum or near global maximum. Yeah, because sometimes you cannot reach there but reach near to it. Yeah, especially when we use numerical solution. Yeah, or global minimum depending on like whether you want to maximize something, like maximize how many contaminants you're going to extract, or minimize something like minimize the cost for a design. And I will show you example for these things. Yeah. Okay. So what did we learn from here? So we learned from here something very important. We learned from here is like all these critical points will occur where the slope is 0. That's like where my f of x is equal to 0. That is where I will get all these critical points. So if I have like my function, that's like my function f of x. If I find like the derivative of this function, and then I said like the derivative is equal to 0, then I will get like all this critical point. But I have a problem here. Yeah. I can know that this critical point is minimum, this critical point is maximum, this critical point is inflection because I'm plotting it. Can I know this without plotting it? Yes, you can. By finding the second derivative, this is called like the second derivative test. So basically, let me explain to you what's happening here. So here you see the slope, like my function is negative, negative, negative. I'm increasing, decreasing, decreasing. Then here it becomes 0, and then here I started to increase again. So let me just draw this for you. So here I have like something like my slope is decreasing, and then here it will become 0, and then here it will increase again. Yeah. So you see how like I'm concaving upward. Yeah, like this. Remember, like if you remember from like previous lesson, I told you like this guy is like the slope, and this guy, the second derivative, is like the curvature. And remember the third derivative, I told you that's called like the jerk or something like this in physics. But this is the slope, this is the curvature. So what in the minimum, okay, just like in the minimum, so the slope here will be negative, yeah, and the slope here, so this is my critical point. Just to the right hand side of this critical point, the slope will be positive and this function will go up. So if my second derivative is positive, like larger than 0, then this is like a local minimum. Versus, let's look at the other case. So the other case is that like my function is like increasing, increasing, increasing. The other case, like my function looks something like this. Like my function is increasing, increasing, increasing. The slope is increasing. Then here it becomes 0. Then here it is decreasing. So here that is positive. Yeah. And just to the right hand side of this guy here, that is negative. Just to the right hand side. So, and that is what? It's like it's concaving down, and this would be like a local maximum. So this is like when it concave up like this, that's the local, that's minimum, and that is maximum. And so basically when I get my the curving, yeah, when I get my second derivative for like this critical point, like for each critical point, yeah, is like less than 0, then this is a local maximum, yeah, that's a local maximum. What about this guy? So like this guy is very interesting because this guy, like I have here a positive slope, so this is positive, it's increasing, but after this guy, so here in this guy, it's positive, it's increasing, but then I here my inflection point, but after this guy is also increasing. So how this thing is, and here the slope is 0. So how this thing is curving? Actually, it's not curving because it is like positive and then positive, so it is not curving. So f of x at like this critical point, if it is equal to 0, this means that this is an inflection point. So here, like this guy is like curving upward like this, local minimum. This guy is like curving downward like this, local maximum. This guy is not curving. That's like an inflection point. And that's how I use the second derivative test. I know like for some of you who didn't study this before, that could be like very confusing and you don't know what's going on. But that's okay. Don't worry. Like with an example, this and with more practice, this concept will become easy and very clear, and you will see how useful these concepts are. Yeah. So here, this is like rule number 1: critical point occur where I have a slope is equal to 0. Yeah, where the slope is equal to 0. That's like the critical point. Rule number 2: I can classify these critical point by substituting them into my second derivative. If my second derivative is positive, which means that like I'm like, so here this is my point, and after my point I'm going up, and like here, so it's like positive, like so I'm curving up. This means that this is like a minimum. If my second derivative is like negative, like I'm going down, yeah, so that is like a maximum. And if here, like I go up here and then I go up here, if like I go up and go up, so I'm not curving, which is like my second derivative, like of like this critical point is equal to 0, then this is an inflection point. So here, that is an inflection point. Yeah, that's an inflection point. Okay, so basically that are the second rule. So here, this is just like a summary of what I did. Rule number 1: critical point occur where f of x is equal to 0. Here, that's a critical point, that's a critical point, this is a critical point. Here, derivative method will not work because this is a singular point. So derivative method will not work here. Like if you have a function that looks something like this here, you might need to use non-derivative based optimization technique, yeah? Like stochastic or heuristic or whatever. Yeah. Second rule: if I evaluated my f of x is less than 0, that's like a maximum point, like here, because I'm curving in this direction. If it is larger than 0, it is a minimum point because I'm curving in this direction. If it is equal to 0, then it's an inflection point because I'm not curving. It's like increasing and increasing. So from increasing to increasing, where am I curving? I'm not curving. Yeah. And that's the meaning of curving, because curving is something that is difficult to conceptualize or visualize. But hopefully with these concepts, I don't know if it will click or not, but yeah, you can think about it. Yeah. Okay, then to classify local and global minimum. Okay, one more thing. So now here I identified here. Let me just lead these things. Like here, I just identified like, so this is a local minimum, this is a local minimum. But what is the global minimum? So to identify global minimum, you need to evaluate like this guy, f of x at the endpoint and f of x at the endpoint. And then you look at the four of them. So this is like the smallest one. So this is my global minimum. Similarly with the maximum. So I identified like one local maximum here, and then I identified my two endpoint. Yeah. And this is larger than this is larger than this. So this is my global maximum. This is my global minimum. This is my global maximum. But you need to, and that's why we find like these derivative. Okay. So I think some of you might be saying, oh, I mean, I don't know what's going on here. With this example, hopefully things will become clear. So I'm telling you, find the global maximum and global minimum and inflection point of this function. So this is an FE problem. Yeah, so I got this last, like one of the FE book, like something similar. Yeah. So this is an FE problem, and I am telling you find the global maximum and global minimum. Like, what would be the solution strategy? To find the global maximum and global minimum, you need first to find like all the local maximum and local minimum. Yeah. Of course, provided that this function is smooth, which we know it is like smooth, yes, regular polynomial function as continuous, yeah. So basically, the solution strategy is to find all local min and max, to evaluate the endpoint and to see like which is larger, like this local min and max or like one of my endpoints. That's it. So, but first we need to find this local min and max. And whenever you get these problems, these type of problems, the first thing you do is just like you find the first and second derivative because you know you will use them. So that's the first thing you do. So basically, and here I'm like defining the interval like from where to where. So I'm defining this from -1 to 2.5, something like this. Okay. So here, the first thing you do when you get these types of problem is that without thinking, you just find the derivative, yeah? So the derivative of this guy, that would be like 3x equal to, that would be minus 6x, and that would be like plus 0. I can take like 3x as a common factor, so I can take like 3x. That will give me like x minus 2. Yeah, give me something like this. And then like what do you do next? You find the second derivative. That goes without saying, yeah? So that would be like 6x, and that would be minus 6. And I can take like this 6x minus 1. Okay, so now I have my first derivative and my second derivative. Then what? Well, I know that like I need to find my critical point. And how do I find my critical point? I know that my critical point occurs when f of x is equal to 0. That is where my critical point will occur. So basically, I get this guy, yeah, and I equate this guy to 0. And now I can find my critical point. So this guy is equal to 0. Now I have like 3x is equal to 0. Then I got x is equal to 0. And I have like x minus 2. I'm finding the root of the equation. Yes, that's what I'm doing. X minus 2 is equal to 0, and that will give me x is equal to 2. So now I have two critical points. Yeah, but I don't know whether this is like local min, local max, or inflection point. I don't know. I mean, I can plot the function, but I don't want to plot the function. I just want to use my, so this is my first derivative test told me that I have like my critical point 1, I have like critical point 1 and critical point 2. Yeah, so this x1, like my critical point 1 and critical point 2. I don't know whether this is mean, max, or inflection point. Can I know this? Yes, I can know this from my second derivative test. How? Because I know I just like evaluate this critical point using my second derivative. So I can say here f of x of like my x, my first critical point, which is 0. So that would be like here 6 minus like 0 minus 1. So that will be minus 6. What does minus 6 mean? I mean, I don't remember these things. I can just like visualize it because I understand like what it like the meaning of curving. So I can just visualize it. So I will say like minus 6 means that like this is my point here. And after this point, the slope is negative. So the slope is negative, which means the slope here was positive, so this is positive, and this is negative. So this means like I'm curving in this direction, which means that this is like a, which means that this is a maximum. This is like local. This means that this is local max. Let me evaluate the second point. Yeah. So my second point, yeah, f of x. See, like these things, like when you see an example, hopefully now it's clear. Yeah. So basically, I just like evaluate this guy here. So that's like 6, 2 minus 1, and that will give me 6. So 6, like the negative 1, yeah, that's like local maximum. 6 means what? Like, so means like this is like my uh, critical point. Like here, this is like my x, see my 1. Here, this is my critical point 2. And then after this guy, it is like increasing. So I have a positive slope, which means that here was like a negative slope, which means that I'm like this would be like a minimum point, and the slope here would be 0. So that would be like a local minimum. Yeah. So this is a local maximum. This is a local minimum. So I'm done. I identified my critical point. Now, it's also telling me that could be a little bit confusing, like find the inflection points. But I don't get any inflection points here. I only got like 2 of them. Like one is like became a local max and one became a local minimum. Like where is the inflection point? Remember, the inflection point does not necessarily require that its first derivative is 0. Sometimes its first derivative is 0, like in this case here, yeah, its first like derivative is 0, but not necessarily, because like for example, this is also like an inflection point, and this is also like an inflection point, yeah. So it does not necessarily require that like the first like derivative is 0. But I know how to find all inflection points, because I know that like inflection points occur when I set like is equal to 0. So let's just set like this guy is equal to 0, like my second derivative. So basically, like I will say like 6x minus 1 is equal to 0. What does this mean? This means that 6x is equal to 6. This means that x is equal to 1. So that is basically my inflection point. This is an inflection point. I can even like plot this function. I mean, it's not difficult to plot this function, because I know here at like, let me just do some plotting, yeah? Because I know here, let's say here, at 0, so I have like something here at 0, I have like something here at 1, and I have something here at, so at 0, that's like my first critical point, x, critical point 1. Here, this is like the inflection point. Here, this is my second critical point. I know at this guy, at 0, what do I have? I have a maximum, yeah? So I have something that looks like this, yeah? Again, I don't know exactly where exactly it will be. Here, I know I have like an inflection point. And here, at this guy, I know I have a minimum, yeah? So I have like a minimum here. So slope here is 0. I have slope, yeah. This is like the slope here is 0, yeah? And then you connect them, and then here, that's like where I got to have like my inflection point, yeah? That's like my inflection point here. So this is like my max, min, and inflection, yeah? Where something like this. Okay, so let's do like, so I plotted it here for you. Does it look similar? Yeah, not bad. So this is just like plotting my oops, where did my table go? I have a table here. Let me bring the table. I deleted my table. Okay, here we go. So we copy. You can, let's just paste it as is, yeah. No problem. Let's just bring this guy down. I mean, I want to. Okay. My mouse is not cooperating. Hopefully it will cooperate. No, does not want to cooperate with me. Let me try again. Can I? How about this guy? Can I bring this guy down? Right. Here we go. Here we go. Okay, this order send to back. Yeah, here we go. Okay, not bad. No, okay, here we go. Sorry about technical issues. Okay. Now I realize is that I have to bring it down. Because okay, here we go. Now we're good. Okay, so I just summarized this problem for you here. So what you see here, this is like your function, your derivative, first derivative, the second derivative of the function. I have like one critical point like at x equal to 0, like here, this guy here. I have another critical point at x equal to 2. I have an inflection point here. This is my endpoint, so I have like this is like endpoint 1, and this is like my x like endpoint 2. So this is my critical point 1, like x critical 1. This is my x critical 2. Yeah. So basically, I want to like see like where is my global minimum and global maximum. That's the question. Yeah. So let's look at this. So this is like my endpoint. Like so, you basically like plug this guy here. You get y is equal to -4. Yeah. See here, like this is what I wanted to show you for my critical point. So this is like critical point 1. This is like my critical point 2. You see here, my first derivative is 0. Yeah. For my inflection point, like this is my inflection point. See, my second derivative is 0. Yeah, so this is basically like one of the key concepts that you all learn. But now I'm telling you where is the global minimum. So the global minimum basically like this is your x, you evaluate your f of x. Let's classify these points first. So here, this is like the first guy, this is just like which is here, this is just like an end point. Yeah. This guy here, we classified him at like 0, that's like critical point. And we can further classify him as max. Yeah. This guy here, this is not a critical point. This is just an inflection point. It is not a critical point because remember, critical point are when your slope is equal to 0. So this is just like an inflection point. Okay, this guy here, that's like a critical point. And that's like a min. This guy here is like an end point. This guy like 2.5, which like this. Let me delete this guy. X is like here. This guy like 2.5. Yeah, that's like an endpoint. Now I'm telling you where is my global max. So the global max, how could you search for this? So you look for your local max. So I have one local max, like I have this guy here. Yeah. So I have like one local max here, yeah. And then you search for your endpoint. So I have an endpoint here and an endpoint here. And you see which one is like the largest. So here, this guy is 1, -4, -3. So this one is the largest. So this means that this is my global max. Yeah. See, this is just without visualization, by just like looking at the data. Yeah. Where is the global minimum? Yeah, so the global minimum, again, it could occur like at either one of my endpoint or my local minimum. I have only one local minimum here, and see like, so I evaluate like this guy is -4, this guy is -3, this guy is -2, so this is the smallest one. So the local minimum is actually this guy. So this, sorry, global minimum, yeah. And this would be just like a local minimum, yeah. So let's say if this is like the functions that I want to optimize, let's say this is the how I want to find the minimum value for like something. So that would be the minimum value, yeah. I want to find the maximum value for this function. That would be the maximum value. Okay. So basically that is what it is, yeah. Uh, Here, this is a practice problem. I will solve this in another video, like a tutorial video. Again, this tutorial video are optional. You don't need to watch them. But here, I just want to just show you like, so this is my function, yeah? This is my first derivative, my second derivative. And then from this guy, like I know that like to find critical point, I said this is equal to 0. So basically, I said like this guy here is equal to 0. And then somebody might tell me, okay, like you said this guy is equal to 0 to find like these critical points, yeah? And again, critical points, that's when your derivative is equal to 0. That's exactly what we have here. Like when this guy is equal to 0, that would be my critical point. Somebody might tell me, oh, how did you do this? I mean, how could you solve this thing algebraically and get like 1, 2, 3, 4, 5 critical points? Well, actually, I didn't. I didn't solve it algebraically. I solved it numerically. So if you are interested, and I solve it numerically with Excel. So and you can do this with your calculator also. So if you are interested in know how to do this with Excel, how to like find the root of this equation numerically with Excel, so you can watch the tutorial. Again, you don't need to. But I mean, this is not the point, like because this like all you want to do here is to find like the roots of this equation. Do it analytically, you do it numerically, you do it whatever way you want, yeah. But here's the point here is that like, so I identified like this critical point, then I verified that all have a slope of 0. And then I did like my second derivative test. So my second derivative test give me 0 here. What does this mean? This means that this guy is like an inflection point. My second derivative test give me like a positive here. This means that this is a minimum. Give me a negative here. This means that this guy is a maximum. Give me like a positive here. This is a minimum. Give me a negative here. This is a maximum. But now I want to know, like without plotting it, like forget this guy, like okay, as if this guy is not here, yeah. Don't look at it, yeah. Without knowing, by just looking at this table, like which is my global maximum. So my global maximum, like I look here at this guy. So like my global maximum, it could be either like one like this guy or this guy, one of these guys. So I look at this guy, this is 2.13 and this is 3.18, so it is like this guy. So that is like my global maximum at 2.8, which is here, and what we have here. Now I tell you what is my global minimum. So my global minimum, you look at the minimum guy. So like you have this local minimum here, you have this uh, local minimum here. This guy gave me negative 0.31. This guy gave me negative 1.18. So this is like smaller than this guy. So this is at 2.19. So where's 2.19? So 2.19, that's here. And that's exactly like my like global minimum. And this is like global maximum. Yeah. Okay. What else? What else do we have here? of course, like if you also need to check your endpoints to make sure. So this is my two endpoints that like you don't like that. So here, like if I check like these two endpoints, like this guy is still larger than both of them. If I checked here my two endpoints, this guy is still like smaller than both of them. That's why I didn't like include. But you should generally like check the endpoint. Yeah. So this is basically, you can watch the tutorial video. I can maybe, uh, I don't even know if this required a tutorial video because I just already told you like the essence of this problem. We will see here. I mean, you just got like the essence here. Oh, no, sorry. I will do the tutorial video to show you like how to find the root of this equation numerically with Excel. This is your homework problem. It is the same as this problem, except that like the range is like here from negative 1.1 to 2.5. It's the same problem, yeah. Here it is like a different range. And again, like uh, the idea of this problem is mainly like, remember, like the whole idea of this course is that you practice this basic conceptual and fundamental conceptual understanding and fundamental skills. So basically what I want to test here, I want to see like, do you know what's the difference between like a local and global minimum? Do you know how to evaluate the function at your endpoints and your critical point, and then like do something like similar to this and things like that, yeah. Okay, so that is I think all for this lesson. In the next, like in another lesson, we will see how to put these concepts of first derivative test, second derivative test, critical points, like to solve like an optimization problem for a simple problem. Yeah, just simple stuff. Okay, so